welcome to the first talk of the year. So tonight we are very honored to have a distinguished astronomer in X-ray astrophysics. He is former president of the Royal Astronomical Society and the winner of many awards, including the gold medal of the Royal Astronomical Society and the 2020 Kavli Prize for astrophysics. Right before the talk, I would like to mention that in case of a fire alarm, the fire exit is at the back over there. And if you need, the toilet is downstairs over here. Right, so without further ado, let's leave the lecture series to Professor Andrew Fabian.
Thank you, it's a pleasure to be here, and I think I've not talked to QAS since about 2012, but I hope you'll enjoy what I'm going to tell you, which is basically a tour through the X-ray astrophysics of the hot and violet universe. So X-ray astronomy is part of, X-rays are part of the electromagnetic spectrum, and you can use all parts of the spectrum to observe the universe. So let's look at the X-ray side. So this is just a comparison. It's not a photograph, it's just a computerized comparison between the optical sky and the X-ray sky, which is has been constructed to be, this is computerized to match this exactly in terms of space. Okay. Now, those of you who are familiar with the sky will instantly recognize the constellation of Orion and the brightest star in the sky, which is Sirius. But if you go in X-rays, so this is, you can see the three stars in Orion's belt in X-rays, but you can't see Betelgeuse at all. And in fact, it's not being detected in X-rays. A big red giant is too cool. X-rays come from stuff which is 1,000,000 degrees or higher, or very energetic particles. So, and there's an X-ray photon has got an energy which is 1,000 times the energy of visible light. So you've got to have energetic processes. This is Sirius, the brightest star in the sky. This is Sirius in the X-ray, but that's its white dwarf companion, Sirius B. It's a binary system, and Sirius B was discovered in the Victorian age and is a collapsed star, a white dwarf. This is the Moon, next to Aldebaran in Taurus, and this in the X-rays is, the Moon is that, okay? It's extremely feeble, but this thing that's really bright is the Crab Nebula, which is the remnants of an exploded star, that exploded in 1054, or was at least seen from Earth in 1054, and contains a pulsar, which is a collapsed star, a neutron star, which is rotating 30 times a second, rapidly spinning, and it's a very bright object in the X-ray band. And most of the other objects are either M-dwarf stars, faintish stars in this picture, or they're accreting black holes throughout the universe, accreting away. That accreting means gathering in matter, which falls into the black hole. Of course, when it's gone into the black hole, you can't see it. It doesn't give out any radiation whatsoever. But on its way, it falls in very rapidly, gets very hot, and radiates X-rays. I started doing X-ray astronomy for my PhD. I had a couple of rocket experiments. This is me there. That's the helicopter that I went out on. Spent a day in this helicopter looking for the remnants of my experiment. As you can see, this is my detector. It's a bit squashed because actually the parachutes didn't work, so the whole thing just fell, free fall, and that's what happens to it. And that was the rest of the experiment. So that was, thankfully, the results were radioed down, so I got my results from this detector, and I was looking at the so-called X-ray background, and so it worked okay. This is, if you go to the switch away from the plane of our galaxy and look out deep into space with an X-ray telescope, this is XNM, the European X-ray telescope looking at about the moon is about this big, apparent size of the moon, and you can see if you stare there, this is what the X-ray background is. It's all these green dots and red smudgy things. The red smudgy things are clusters of galaxies of the order of maybe 1,000 galaxies that form, they're gravitationally bound into a unit. These are the largest, most massive gravitationally bound objects in the universe. They actually have a lot of gas in, and that gas is in there, and it has a temperature of maybe 10 to 100 million degrees and radiates X-rays. So I'll get to those in a minute. The other things, most of the other things, are AGN, Active Galactic Nuclei, which are black holes at the centres of galaxies, which are accreting matter, and I'll talk about those as well as I go on. So that's what it looks like. There's lots to see, but hopefully this can carry on. This is now going to the Perseus cluster of galaxies, which is a relatively nearby cluster of galaxies. It's only 300 million light years away, or 100 kiloparsecs, megaparsecs away. And this is the centre of it, the Perseus cluster. All of these galaxies you can see around. This is my favourite galaxy, NGC 1275, which I'll talk about a bit more later on. Most of the galaxies in the centres of a cluster like this are not like our own sort of spirally galaxy. Most of them are these big elliptical galaxies, just balls of gas, balls of stars. If we now go on from this, here we are, go into an X-ray image that was made of the same region, it looks like this. Here we're looking at the gas between the galaxies. We're looking at gas which, as I said, is like, this gas is about 50 million degrees hot, and there's more of the baryons in a cluster, more of the ordinary particles in the cluster in hot gas than there are in all the stars in all the galaxies that you can see. So this is where most of the matter is. That's normal matter in a cluster of galaxies, is actually in this hot gas. And there's something else there which is called dark matter, which is holding the whole thing together. And the fact that you can do all the calculations of how much gas there is there and how hot it is enables you to actually work out what the total mass of the cluster is, and also how much dark matter is. And so it turns out 15% of the mass of the cluster is in terms of ordinary gas, baryons, and then 85% is in dark matter. And we hope that doing X-ray observations of clusters could actually help us understand what dark matter is. And I'm sure you've all heard of dark matter, and it's something that we don't know what it is, and we know it's there. It has to be there to hold this together. But all it seems to respond to is gravity. All we can detect from it is a gravitational attraction. We can't actually detect anything else from it. Every now and again, people claim to discover something about it, and then it's ruled out a few years later. So this galaxy cluster has got it's got some action at the centre I'll get to in a minute, but also has a big swirl to it. And that big swirl is due to the gas sloshing around in the gravitational potential well. So the gravitational potential well is a little bit like a wine glass. You know, the gas is sitting in this well, and if you slosh the glass around, everybody who's had a wine glass will have done this, it sloshes round, and this is causing this sort of spirally structure here, which you can see there, and creates what we call cold fronts. I'm not going to go into that in detail, but you can see structures there. And this is 50 kiloparsecs, 150,000 light years in dimension, and is slightly bigger than our galaxy, our own galaxy. So we're talking about a very large region here. Right back in the centre, what we see here is, and this is the centre of what I've just shown you, there are sort of two cavities, one there and one there. There's also something out here and something down there. And this is all being produced by radio jets that come out of the nucleus, which point north and south and fill up or create these regions by pushing the gas away into cavities. And those cavities are buoyant and rise up in the cluster itself, there and down there. And this is where the radio emission is, just as I talked about. And the X-ray emission is in the blue, in the red, and a radio emission in the blue, and things sort of fit together. So what's happening is the black hole at the centre is blowing out jets of very energetic material, which is then inflating cavities either side, pushing the gas out and making bubbles. And those bubbles then are buoyant and rise up in this atmosphere and sort of just rise up and go further out. This is another picture of it. And what we've done with these things is you can compare the amount of power in these bubbles. We can work out what the energy in the bubbles is from their volume, and also what the pressure is, which we can measure from the X-ray spectrum. And we can then work out a timescale on which they must be bubbling, and you can get a cavity power and compare that with the luminosity you're getting from the X-rays. When it's emitting the X-rays, the gas is actually cooling. It's losing energy in creating the X-rays we see. That's an energy transfer to us, and obviously out of the cluster. And what we see is a comparison between the luminosity, that's the amount of power that's coming out in radiation, versus the power that's being bubbling. That's not a bad correlation for an astronomer. Okay, so there's, you can see it's many orders of magnitude up on these axes, and when you've got something that's got a high cooling luminosity, it's got a high cavity power, etc., etc. So, and there are all these bubbles in other objects. But this process is something that's still ongoing, trying to understand it, and it's called AGN Feedback, which I'll talk a little bit more about later. But one of the key things that we've been wanting to find out is how is the energy transported in the cluster? How is energy getting out there from the centre out there? The bubbling is taking place, but is that really how the energy gets out? Because the bubbling is taking place along one axis, but what about everywhere else? And one of the things I noticed something like 23 years ago with these images, which I was the PI for, was how ripply it looks. And I started to raise the possibility that there are sound waves going through this gas. Okay, so you've got the gas in the cluster, why not have, and you've got this bubbling taking place. That means you're creating pressure waves, and those pressure waves can then expand outwards, and they will of course be sound waves. So not everybody likes the idea. The other possibility is it's all turbulent motion. Turbulence is sort of, you've got bubbling going on, and maybe it's churning stuff around, and these bit of gas hits that bit of gas, and so on, moves it around, and you get so-called turbulence, like you get out the back of a jet and so forth. So they're sort of, sound waves are sort of quite nice and peaceful, and turbulence is a noisy process. If these are sound waves, they are extremely low frequency. They're about 1 cycle per 10 million years. Now, in space, no one can hear you scream. Everybody knows that. But actually, if you scream on a very low frequency, it is a sound wave, okay? But you've got to compare with the time in which the collision time of the particles in the gas, okay? In this room, of course, the particles are extremely close together. There's 10 in the air, there's 10 to the 20 particles per cubic centimetre, something like that anyway. We're talking about gas where per cubic centimetre there may be 1 particle. So, but nevertheless, you can get sound waves propagating out through there. So that's something that's ongoing that we're trying to understand. Now, one way in which we can understand it is we need to make an accurate spectrum. We want to look at emission, look at the lines, emission lines that we can see, and see whether we can measure the velocity of the gas. What we can do is make use of an X-ray calorimeter, and this is something that's been ongoing for some time to do this. And what you want to do is have a very accurate measurement of the energy of the X-rays when they come in. And here, example, you take the X-ray photon, it goes into an absorber, heats the absorber up slightly, and you've got a thermometer, not really looking like that, but an electronic thermometer to measure what the temperature is, and you then leak that heat away into a heat sink, but you get a pulse of in the rise of temperature, and it looks like that, and then that will tell you what the energy is of the photon that's coming in. Now, in order to make that work properly, you have to put in a very cold bath. And in fact, the detector that I'm going to talk about for the X-ray calorimeter operates at 50 millikelvin. That's 50 millikelvin. It's way down, very, very cold. Also, with X-ray telescopes, you can't reflect X-rays off normal incidence, which means, in an optical telescope, you'll have a telescope mirror like that. Light comes in and reflects off it normally, just goes like that. The only way you can reflect X-rays is with grazing incidence. That's very similar to skimming a stone on a pond. So you need to have the light coming in at less than a degree to the reflecting surface, and then it will bounce off. So that means you end up with lots of little bits of metal. Each of these will be a part of a parabola going inwards, and the light is being reflected off 1624 reflectors down to a focus somewhere, say 3 meters away down there. So doing X-rays, measuring things, is difficult and complicated. What we did back in 2016 with a satellite called Hitomi was to measure, this is again the Perseus cluster, we took a spectrum of it, and we can see these emission lines of ions in the hot gas. And they're very sharp lines, and the width of the line is telling you what the velocity of the gas is. And what we found was it was only 160 kilometers per second, which is much less than the sound speed of gas, which is 1,000 kilometers per second. So it's telling you that turbulent energy is only a few percent and isn't really what we want in terms of doing this feedback. And this was a triumph back in 2016. I was in Japan at the time making the first of these spectra, and the satellite had been launched just a few weeks before. And unfortunately, the satellite had a hitch and ended up spinning out of control 3 weeks later. So that was all the data we got from the satellite. But that's, when you do space astronomy, it's not all straightforward and easy. We now have another satellite called Prism, which is a copy of Hitomi, or parts of Hitomi anyway, and that was launched 2 years ago and is now working brilliantly. Here's another object, another cluster, where you can see these bubbles in it. It's got a pair of bubbles in the middle, and then it's got bigger bubbles there. And you can see this is where the radio goes. And that has this spectrum similar to what I've shown you before. And this is only 164 kilometers per second. It's almost exactly the same value. And so this is brilliant that you can actually detect the motions of these things and look for turbulence and so forth. And we're still getting a little bit of a battle in terms of, is it turbulence or is it sound? Okay, but just to make the point, and you don't have to read all this, I just want to make a point about sound transferring energy, that basically if you were to transfer energy in random motions, that's what I've got in that equation there. Random motions can transfer energy outwards. But if you've got a sound wave, what's important with a sound wave is the displacement velocity amplitude. The energy travels at the speed of sound, which is 1,000 kilometers a second, but what you've got to measure is the displacement velocity. And when I talk with you, what's happening is my larynx and so forth is causing vibrations in the air, which are then propagating out to you. And the air is vibrating by, you'd have to measure it in nanometers. Okay, it's very, very tiny little fluctuations. But when you've got, 10 to the 20 particles per cubic centimetre, and they're all doing exactly the same thing, then you can imagine that energy is being transferred out. Okay, so that's why the equation ends up looking like that. So they can transport twice this ratio of the sound speed to the random velocities in terms of more power. So this, I think, means that sound propagation is a great thing to do. But there's only a minority of us are pushing the sound idea, but we'll have to see how it develops. And of course, sound is something that there's no reason why it shouldn't be there. Another issue I want to get to is looking at the centers of these clusters, where, as I told you, they're emitting a lot of radiation, and the radiation is causing the gas to lose its energy. It's cooling. And there are, if I look at the time scale on which the gas is cooling, it gets, as you go closer to the center, it gets shorter and shorter. So this is radiative cooling time in gigayears, that's billions of years, versus the distance from the cluster center. It gets shorter and shorter as you go in. And this, some long time ago, several of us were thinking about what's going on here, and the gas should be flowing inwards, making what's called a cooling flow. And that fits in with the fact that the images have got big spikes in the center, and this object doesn't have a cooling flow, it just got a very small bump. So the gas should be cooling, and the big question is, what does it do? And some early X&M observations suggested it wasn't working, because we should have seen emission lines from iron. This is iron 17, as it's called, which is iron that's neon-like. That means it's got its electron configuration looks like neon, but of course there's this massive nucleus in the center. Anyway, it looks like it didn't work. But I've been pressing on more recently on this object, the Centaurus cluster, which is another cluster which is actually closer than the Perseus cluster, and you can see there's obvious signs of these bubbles with a diminution and flux around here, and the nucleus is in here. And what we find is that the rate at which mass is cooling is dropping inwards. And the question is, can it be explained, this is again me suggesting it, by X-ray absorption? And this could be the reason that we're not able to see the emission lines. So this is a very complicated picture, but it's X-ray data. It's a spectrum of one of these objects, and these are the emission lines, that one and that one, due to iron 17, and this is oxygen 8 emission. And so from these spectra, we can tell how much gas is at different temperatures, and also we can see if you've got cold gas in the object, it can absorb the X-rays, and you can construct a model of it which is fitted there, and we could work out what the rate of gas cooling is in this object. And it turns out to be somewhere like 15, 16 solar masses a year, which is not insignificant. And because if you let it go for 1 billion years, you end up with a big total. And this was the picture that was right on my introductory slide. This is the centre of the Centaurus cluster, imaged by Hubble Space Telescope, one of my other images from Hubble. And this is the nucleus here, and it's got all this dusty stuff. You can see there's dusty absorbing stuff around, and this emission from that is coming out in the far infrared band, and it fits together with the picture I'm saying. And that's just another picture added to show the contrast in, you can see there's absorbing material all over this place. And also, excitingly, there's a sort of funny little S in the middle. I think that's, the nucleus is right in the middle of this, so it's gas swirling round and presumably going down the hole into the black hole at the centre. And this is just showing you other objects that are doing this, and you can see the centres have got a lot of activity going on. And one of the things which generally, if you've got a talk by an optical astronomer on elliptical galaxies, they would tell you that they're red and dead. And I'm saying no, they're not, okay? Because when you look with an X-ray telescope at the centres of them, you can see processes just like what I've just shown you. So anyway, that's, and what I'm doing exactly at the moment, tomorrow evening, is the deadline for James Webb Space Telescope observing proposals, and with some colleagues I've worked out that there's a line due to neon 6, that's ionized neon, which is emitted at 7.6 microns, and that it's detectable, should be detectable. So I can test what I just told you by looking with the JWST, but unfortunately JWST is incredibly competitive. They'll probably get 20 times more proposals than they can deal with, and so there's a 5% chance of getting my observation done. But anyway, that's what I've been spending part of today, and I'll spend part of tomorrow doing, is finishing this proposal. So not only X-rays, one has to get on with other things. Now let's move on and talk about the other objects in the sky, the active galactic nuclei. These are black holes with material swirling around them. Now, why is it swirling around? Well, everything's got angular momentum. There's relative velocities between everything in the universe, and that means there's angular momentum. And when gas falls inwards, it ends up, if there's a central object, it'll end up circling around it. It's very unlikely to go exactly radially in. And then friction can lead to material moving inwards. It then moves inwards and gets hotter and hotter and hotter, and all sorts of action can happen due to magnetic fields. And this is just an artist's impression of what an active galactic nucleus looks like, with a black hole and a swirling disk getting hotter in the centre. It's sort of indicating it's going to sort of yellowish, but the temperature will get very high, and the magnetic fields may end up twisting and making some sort of jet, and there may be a very active region around about here. That's the kind of thing we infer. Now, what's going to come out from these areas are X-rays. A lot of X-rays are going to be present, and that's what I'm interested in. Now, in terms of the amount of energy, everybody knows the formula E equals mc squared. I hope you all do. But that's energy, mass converting to energy. Well, the chemical, when we're in a chemistry lab, chemistry is extremely low energy, and it's roughly 5 × 10⁻11. It's very low in terms of efficiency of converting energy into matter. So petrol, when you get energy out of petrol, it's going to still, there's a mass change, don't worry, everything is conserved, You can't get something for nothing. Nuclear fusion is the jump then up to is 100 million times more energy efficient, and you get 0.05 mc squared. But you can get another 20 by going up to black hole accretion. If you were to take matter and drop it in a black hole, you get out 10% of rest mass in terms of energy. And as I say, it's 20 times more than you get out of complete nuclear fusion. So you could imagine having a car where you drop little tiny drops of water in or something, and it takes you billions of miles, but I don't know how we'd ever make anything like that. So that's what we've got. And that what we're doing here is making all this accretion matter falling in and producing that. And what we are battling with is to understand what we're seeing when we look very close to the centre of one of these objects. There appears to be a corona above the centre of the disk. And it could be something like that, or it could be something, a failed jet or something more compact. Okay? But what we're dealing with, this is the solar corona around the sun as seen during an eclipse. And this is the power, the luminosity that comes out. And I'm sorry I got it in ergs per second, because astronomers all use ergs per second. And I think that everybody else in physics and chemistry and everything else forgot about ergs many decades ago, but we're still there. If you want to turn it into watts, just take away 10 to the 7, or divide by 10 to the 7. So it's less than 5 times 10 to the 20 watts. But one of these coronae has a luminosity that is at least 10 to the 10 billion times larger than the solar corona. And it could even be, something like 10 to the 8 times more powerful than that. That's a very low luminosity corona. This is a high luminosity corona. So we're talking about an extreme, enormously high energy efficiency or energetic, powerful region, which is actually very close to the black hole. And it's curious, we end up with the most luminous objects in the universe are directly next to the darkest objects in the universe, namely the black holes. And what you've got to do is imagine that's spinning round. The sun spins round once every 26 days at the equator, and more like 30 days at the poles. It's differentially rotating, and it's got that power. Now imagine one of these coronae regions, and for a million solar mass black hole, the corona has a size which is not much different from the solar corona, excepting it's rotating on timescales of minutes, not months. Okay, and so you can imagine that the magnetic fields might do something more dramatic. So that's what we're dealing with. And what's been realised is that all this energy coming out from black holes can do something to the galaxy itself. Because the energy released by the growth of the black hole, so if you've got in the middle of a galaxy, imagine you've got a 10 million solar mass black hole, then you've got, in terms of energy that's being released to generate it, must be the equivalent of a million solar masses of energy. And that is 100 times the gravitational binding energy of the galaxy. Okay? So, in a sense, you might say, well, why do galaxies exist? Well, why? But the problem is, how do you link that energy, which will be coming out as X-rays and very powerful radiation, how do you link it to all the stars in the galaxy? It's not to push the stars out of the way. The stars are very dense and have got very small cross-sections. They're very tiny compared to all of this. So we've got to think of a way they can connect. And the way they will connect is through they will connect to the gas in the galaxy, and they can significantly affect how the gas performs in the galaxy, how it evolves. And in that way, this tiny thing in the center of a galaxy can actually affect the growth of the galaxy and determine what goes on. And the key point about this is not necessarily looking at the energy. You have to also look at the momentum. Just to sort of remind you that the rocket science is difficult. It really is difficult. And essentially, rocket science involves momentum and forces. Okay, there's enough energy in a full car full of petrol to take that car up to 50 miles or so vertically. But I challenge you to do it, get it to work. And of course, you all know about rockets, how you stage them and so forth, in order that they can go very high. But what we've got to do is think about momentum. Now, one thing that has momentum are photons, and photons can push things. And this is a simple argument due to Eddington in terms of, imagine you've got hydrogen gas. There's an electron and a proton. Hydrogen is just an electron and a proton. There's lots of photons coming out like this. The photons will interact with the electron and not so much with the proton. In fact, all the radiation is going to push on the electron, not the proton. So we can write down an equation. This is the force of gravity acting on the proton, and there's a radiation pressure which is given by this, which is just the photon flux times the interaction cross-section, which is called the Thomson cross-section, times the momentum of photon, and you can equate them and you get this equation. So, and it's called the Eddington luminosity, because Eddington, who was a great astronomer 100 years ago and lived in Cambridge and worked in Cambridge, the luminosity, the Eddington luminosity is proportional to the mass of the central object times all these fundamental constants, the gravitational constant, the mass of the proton, speed of light, and the Thomson cross-section. So, just to show you radiation pressure, that happens to be a galaxy, but it's too far away to do anything. But when you go from this, look at a comet, they have two tails. One is a dust tail, and that's driven by radiation pressure. That's the radiation from the sun is pushing on the dust. It's being absorbed by the dust particles and scattered by the dust particles, so they're being pushed away. And radiation pressure acting on dust is a very powerful way to shift gas around. You can also have a wind, and the solar wind is giving rise to this other tail. So the radiation pressure and winds are important in terms of what's going on. And if you've got a very powerful source of energy here, you can get a large outflow. And I won't dwell too long on this slide, just comparing in terms of lots of galaxies. There's a region which is forbidden where you don't see things, and this is indicating there are outflows. I'm not going to go into the details of this because it will take too long, but I hope you've got the idea. Energy release is electromagnetic radiation, which is going to give rise to jets and outflows. And it's also possible that in an outflow you can get stars forming. We've seen evidence that they can form in the outflow, and that way they can grow parts of the galaxy which would not have grown otherwise. And so it's possible that the black hole at the centre can actually change the growth of a galaxy and the shape of a galaxy. And this AGN feedback is something we've realised over the last 25 years, and it's profound in the sense that physical size of the black hole in the centre, which is in controlling it all, can be the size of the sun or something, but it's controlling something so much larger, and it's surprising. Now I'm going to go a little bit into something else about accretion disks. I'm going to go on about how we learn things about the accretion disk itself, how we learn about what's happening right down the central region. And this is something where the corona above the accretion disk, which is like this bit, sends radiation to us, and it also sends radiation onto the disk. So the disk is irradiated, and some of it will scatter back up, and that's called the reflection spectrum. It's not true reflection, but it's just a word for it. And what about if, when I'll just go back again to this. What can happen is if the disk is coolish, it can create fluorescence of the disk itself, and the disk can emit lines that have been excited by the radiation illuminating it. And if we have a line emitted from a disk of material, then if you're in the Newtonian physics, and this is plotted against frequency, you get the old Doppler effect, where the parts coming towards you are going to be blue shifted, and the parts going away are going to be red shifted. But if you're around a black hole that's going up to half the speed of light at the innermost radius, and then you've got special relativity, and that means it beamed on this side, it beamed towards you, and the side going away, it's beaming away. And then when you put general relativity in, there's the gravitational redshift, because the photons have got to climb out of this deep potential well, so it all gets shifted to the red, to the left. And so the whole irradiation of this bit is going to lead to a line that's skewed like that. And this is what you get with a non-spinning black hole, and this is what you get from a spinning black hole. And this is something I contributed to a long time ago, and started to look for it, and it was difficult. But there was a satellite launched in 1995, a Japanese-US satellite called ASCA, and I managed to persuade them to look for 200 kiloseconds at this object. It's the name of the object, and we ended up getting this spectrum out, which is a bit like this. Okay, okay, here it is, just there. And this broad iron line, as it's called, suggested we were looking at material which was very close to the black hole. Now with this new satellite, CRISM, we are able to get much more precise observations of this. And this bit of the spectrum is, you can see from the 8 to 4, is looking at this bit. We can see it's got a spiky inner part, but you can see very clearly it's got this broad base, a broad iron line. So it's been confirmed with CRISM, and this is also, this bump here is called the Compton hump, is what you expect as you go to higher energies. And this result was published this week, so taking you up to date. So one of the things you have to do if you're an astronomer, you have to have patience. I mean, I came out with the idea of broad iron lines in '89. Okay, it was 1995 we found the first one, and now we're confirming it with a new instrument here. I mean, I've got 2024, but actually the paper, that's when the paper has been published on Monday. So it's you have to, as I say, keep going. And sometimes the emission comes from very small regions. This is one spectrum from a student of mine measured, where the blue is what you'd expect the spectrum to be if there's no relativistic effects. And what we see in the data is it's blurred and pushed to the left. And that's the gravitational redshift, because we're looking very close to the black hole, so gravitational redshift is very large. Now, all of you have probably heard of the gravitational redshift effect. It's as you go, if you take a clock and you raise it and look at it, it appears to go run slower. And it's actually, corrections are made with GPS satellites in order that your GPS on your phone or in your car operates properly. They have to include the gravitational redshift effect. If it was not included, errors would be like about 7 to 10 miles a day that you would get it wrong. Okay. Initially, the engineers refused to include gravitational redshift effect, thinking it's completely irrelevant. But that's a general relativistic effect which operates all the time for us and has to be included. This is much, much, much larger effect that we can see here. And these observations are possibly the closest observations to the horizon of a high-spin black hole. That's what the spectrum looks like from a neutron star. And we can start to measure the spin of black holes. This is just a black hole spin is measured to 0.1 in its units versus the mass of the black holes. And you can see quite a lot of them seem to be rapidly spinning. The important thing is that if this is a no-spinning black hole, the black hole is there, its innermost stable circular orbit is at 6 gravitational radii, 6 times this one here. As it spins faster and faster, this comes in, and by measuring the inner radius, it enables us to work out what the spin is. What about the plunge region? This is the closest region of the disk to the black hole. Okay, it's where sort of simple physics breaks down, and it's this so-called ISCO, innermost stable circular orbit, which has been known for a long time that it must be there, and basically what the simple physics says, everything spirals round, it's losing energy because of friction, and moves in, and once it gets to the edge here, it then goes onto a plunge orbit. It's still got angular momentum, but it will go around and then plop into the black hole, and all of these innermost bits, they don't collide, and you don't get any more radiation out from inside. So you can't look inside the plunge region. Well, it's a bit like this. You know, if you're in the disk outside outside the ISCO, you can imagine being in a canoe here. You might just about be able to paddle away, but once you've gone over there, paddling is not going to be much help to you. Okay, so but I back in 2018 had data from an object that flared up in our galaxy, which was a black hole with a star in orbit around a star, and the star was dumping matter onto the black hole, and angular momentum meant there was a disk and everything. And I looked at the spectrum of the disk, and I got this spectrum in black here, and I fitted what we think is a good spectrum that you could predict for a disk, and found out there was something missing. That it didn't actually work very well here. It needed a bit more energy and a bit more radiation. And I guessed that it might be due to emission just within the ISCO. And after about 5 years, that I had about 5 citations to that paper, people didn't seem to like it. But you have to keep going, just keep on going. And then a very bright guy from Oxford came along, a theorist, a mathematician, Andrew Mummery, who was working on what happens at the ISCO, and he was sure that, of course, we would get radiation from that. And he came up with his calculations, which he called full Kerr, Kerr being the name of the spinning black hole after Roy Kerr, the New Zealander who came up with the equations for a spinning black hole. He's got full Kerr, so he's convinced he's got the right answer, and it gives a very nice fit to that. So we've started to look at emission from the ISCO, at least that's what I think, and hopefully everybody else will think so too later on. So what about X-ray astronomy in the future? We were hoping that the PRISM I've talked about several times, this satellite, Japanese-American satellite, which was launched 2 years ago, and it's got this calorimeter which operates at 50 millikelvin, and so has to be in a dewar, like a thermos flask, and has to have a sort of valve on the top. And in order to operate it on the ground before launch, it had a valve, a door that came on the front of it. And the idea was the door would open once everything had got launched and they'd allowed to let things out, gas a bit. They would then open this door. It's called the gate valve. It's only about this big. And unfortunately, it hasn't opened. Luckily, the gate valve is not completely opaque to X-rays. It's made of beryllium, and it's got a grid of wire on it to hold it in place. But nevertheless, we got these wonderful results, even with this gate valve closed. But that means we can't see the soft X-rays. And they tried 2 years ago to open it by triggering it and so forth. And the problem is there was some elaborate device to open it, and that basically that something should slide out like that. But unfortunately, it's got a cable on the end, and that's obviously hit the edge and is stopping it opening anymore. So what they did in September, just a month ago, was they spent 2 weeks repeatedly making the balance, that there are some balancers inside the dewar, the cooling system, that can help keep the helium cooled in there, and they were swinging them to and fro in various phases and so forth. And also they lined the satellites so that the temperature was as high as possible. They dare allow it to be, but it hasn't opened, so that's a pity. Maybe it will open later, I don't know. But again, this is part of this kind. I want to emphasise with astronomy, some things work, and I'm truly amazed by the JWST, which has got zillions of modes and everything else, and they all seem to be working perfectly. And it had this folding out mirror and everything that many of us thought wouldn't work. And of course, everything worked and worked perfectly, and it's absolutely brilliant to use it. But then you get other things that don't work. But anyway, I'm PI have a proposal to get 3 more megaseconds of Chandra data. That's the telescope that made those pictures of the Perseus cluster. I know we've only got 1 megasecond on it. I want to get another 3 megaseconds to look for the sound waves, and that's been approved. But guess what? In the US, it's not clear what's happening in NASA. It's not clear that Chandra will carry on operating. They've more or less agreed that JWST will carry on operating, but it's not clear what most of the other satellites are going to do. And I've got my fingers crossed, but we don't know. Continuing operation of XMM stars. So China's going to launch a satellite in 2027, and we hope that NASA will select and fund a new X-ray telescope that is being designed in 2032, and then in 2037 ESA has got plans for a very large telescope, X-ray telescope, which hopefully will happen. So I've taken you on a tour through X-ray astronomy, and thanks for listening.
Thank you very much for the very, very nice talk.
Okay.
I have this catch box here for questions. So does anyone has questions? Let me try if I can get it over there. Just talk right into it.
What?
Just talk right into it. Yeah, just talk right into it.
Just talk. Oh.
Yeah.
You mentioned you had a favorite star system, I think, at the start of the talk.
Yes.
Why is it your favorite?
I'm sorry. I mentioned that I had a
Favorite star system or galaxy or something at the start of the talk, I believe.
infrared. Yeah. I'm not sure I'm remembering.
Favorite cluster, maybe?
Yeah.
Favorite galaxy. In the picture, remember there was all the elliptical galaxies, and then there was the one that kind of looked like a spider.
Oh.
Thanks.
Yeah. That's NGC 1275. Yes. Thank you. Yes. Yeah. It's got the red sort of. Those are filaments. That's a name for them, and exactly what they are. I also received, and somebody said, "Do I want to join their proposal on looking at the filaments with JWST?" And we've looked at those filaments a lot with Hubble Space Telescope and other telescopes, and they appear to be molecular in nature and atomic, and they're obviously magnetized, and I think it's somehow the bubbling process that's taking place in the cluster is dragging stuff outwards and forming these filaments, but there are mysteries, what I would really say, because I could go on for hours, but you wouldn't know much more at the end of it.
Any more questions? Can you throw the box to the front? Oh.
So you were indicating that the idea of sound waves was not well accepted by the community.
Sure.
What's the objection to it?
I don't know. I mean, we have. It's generally accepted that there were what are called acoustic oscillations, which is another word for sound waves. And if you work in cosmology, you'll be very familiar with baryon acoustic oscillations, which is just a pompous way of saying sound waves in a ordinary gas, right? And it's something where before the universe was recombined back around 300 million years. Before that, it was highly ionized gas with sound waves propagating through it, and everybody's happy with that. I don't know why people don't like the idea of sound waves operating locally, and it's something I've grown to understand is that matter is sometimes if you tell people in more detail about why you think it's this way, they'll go further and further away in the opposite way. So I don't know. Thank you for the question.
Any more questions?
So earlier you showed a picture of yourself doing your PhD.
Yes.
Yeah. The experiment that you were showing
Yes.
and the PhD as a whole, the project as a whole,
Yeah.
at the time, did you consider it to be a success, a failure, even though, or if that's even a term that you would use for a project such as that?
It was a success because of the fact the only reason it had a parachute was to collect the mildly radioactive source that was part of the package, which I'd used to send X-rays. It sent X-rays into the detector all the time in order to sort of make sure that it was operating. All the data was radioed down, and so I got a nice paper out of it. So I would count it a success. And I did have I had two rockets in my PhD. One was from Woomera, the other one went from Sardinia, and these were Skylark rockets, as they call them. And that one, the parachute didn't work either. So anyway, but I got the data. That's what counts. Yes.
Any more questions?
You mentioned earlier in your talk that, you mentioned earlier that being an astronomer requires a large amount of patience.
Yes.
That it takes lots of time to get your theory accepted and you face lots of resistance. In your view, do you think that this instead makes the work you do more rewarding in spite of the amount of patience it takes?
I must admit, I feel like I've had an extremely rewarding career, and I've enjoyed myself a lot, and I enjoy doing the work I do. Yes, it's great if you do something and everybody says, "Oh wow, fantastic," But it's sometimes good to be, you end up realising you're the only person in the world who knows what is happening in that thing over there. That can be quite good as well. Okay, so I mean, yeah, I maybe I play too much on the negative aspects of things, or about how not everybody believes this or whatever. But generally, it's been good, and I think in science it doesn't work by somebody doing something and everybody sort of says, "Oh, hooray! Let's all," that's obviously it. People, there's always a lot of it may be this, maybe that, and so forth.
Any more questions? So I have one more technical question at the end. So in the beginning you mentioned that the ripples are either, so there are two main, it's either turbulence or sound waves.
Yeah.
What's the main reason that you decided it's not turbulence, but it's highly likely to be sound waves?
Now it's because we don't measure a large enough turbulent velocity to have enough turbulent energy to do this. But before we've got these calculations, the observations, I thought that sound waves looked interesting, but I think one of the challenges is that and this is partly why some people don't like it, is you need the sound waves to dissipate their energy, okay? And basically, if this is just a hydrogen gas, it doesn't have any bulk viscosity, so there's no way of dissipating that energy. But my rejoinder to that is an ionized gas full of cosmic rays and magnetic fields. And I think if you send a sound wave through that, you can get geometrical changes in the orientation of the magnetic fields and so forth. So you've got that energy turns into sort of other energy, which is essentially dissipation, which can then, when that's released, it comes out as heat. So it's something to do with plasma physics, which we really need to push at, and plasma physics is difficult.
Thank you very, very much for the amazing talk, and final round of applause.